Hi students, here we're going to be talking about doing the chain rule but in reverse. We often call this U-Substitution because we're going to use the letter U to replace complicated examples for us. Alright, so now we've got to do a little bit of work in terms of going backwards with some functions. We've played around with this sum and now we're going to see this again. So we're trying to find a function whose derivative is 7x squared. We've talked about this in terms of going backwards for this already. And here we have a polynomial, so we're going to use the power rule, but backwards. That means I'm going to add 1 to this. So we got 7x to the third power, then divide by that new power. I'd also like to remind you that we can add any constant to this, so we tend to write this as a plus c. So that's talking about this, is this a unique answer or not? And the answer is no, because if we did this as plus 2, that works. If I took the derivative of this, that 2 goes away, so that's okay. If I did this as, I don't know, plus 3, same thing. Plus pi, same thing. So that's why we have to include that plus c as part of our antiderivative thing. Same thing for cosine of x. So this one's a little bit straightforward. What has a derivative that's equal to cosine? Well, I know sine of x has a derivative that's equal to cosine. And the same type of thing, we could have this as plus 7. We'd get cosine anyway. So we tend to write this as plus c. And then finally, this one's a little bit tricky. This one was written in this format so that we don't immediately try a power rule. And we have to think about what function has a derivative that's 1 over something. And I know that the derivative of ln of stuff is 1 over that stuff multiplied by the derivative of stuff. I'm running out of room here, so I end up with that on a different line, but that's okay. So if we think about this as maybe 1 over stuff, where x minus 2 is that stuff, it might make sense that this is an ln of x minus 2. Let's check this out just to make sure that this is right. So the derivative of ln of x minus 2, okay, that's 1 over that stuff, x minus 2. And the derivative of x minus 2 is 1. So that worked out pretty well. The derivative of that gave us 1 over x minus 2. Therefore, we found our function. And again, we could add any constant to this, and we end up with the same derivative after we take it. All right, so now we got to go a little bit harder here, because now we're doing the same thing, but we're going to be adding some complexity here. So we're going to review some stuff as far as chain rule. And first we're going to take the derivatives of each of these things. So if I do, okay, the derivative of sine of 4x minus 5, well, that's going to be cosine of 4x minus 5, and then multiplied by the derivative of the inside. The derivative of the inside is 4. For the second one, that's going to be 3 times 5x minus 2 to the second. And then times the derivative of the inside. The derivative of the inside is 5. And then the last one, that's going to be e to the 3x squared minus 1. Then times the derivative of the inside is going to be 6x. So in each of these cases, we had to multiply by the derivative of the inside in order to get this to work. We've got to go backwards here in order to make sense of what's going on here. And we're going to kind of explore this a little bit. We're going to play with this going forwards and backwards to try to make some sense of what's going on. So looking at the first one, we're trying to find the antiderivative of cosine of 4x minus 5. And we might start out by saying that this is going to be sine of 4x minus 5. And that's certainly on the right track. However, if we were to do the derivative of sine of 4x minus 5, we end up getting that same thing that we had before. Cosine of 4x minus 5 times 4 because of that chain rule. So that's not the same thing that we have inside our integral, and that's kind of weird. Our goal is to then figure out how can we change this function so that we get cosine of 4x minus 5 instead of cosine of 4x minus 5 times 4. And the answer for that might be dividing this whole thing by 4. So I'm going to rewrite that as 1/4 sine of 4x minus 5. And when I try to take the derivative of that, I get 1/4 cosine of 4x minus 5. And then derivative of the inside is times 4. My 1/4 and 4 cancel out, which gives me cosine of 4x minus 5. Okay, so just to kind of jump backwards and talk about what we just did, we found a function whose derivative was the stuff on the inside. That was our goal. And that function was 1/4 sine of 4x minus 5. I'm just going to throw a plus c at the end there. Cool. We're going to come back to that. Same thing going on for the next one. I'm going to start out kind of in the same way. I know that for this function, this had to have come from something like 5x minus 2 to the third power, but I don't really know what else is going on here. Okay, and this would actually be the third power divided by 3 if that were using the reverse power rule. Okay, so let's do the derivative of this just to kind of see what else is going on. So that 3 would come down. We'd get 3 times 5x minus 2 to the second over 3. Those cancel out. But then we have this chain rule, so times the derivative of the inside, which is going to be 5. When I take the derivative of the function that we started with, we end up getting that extra 5 in there. So 5x minus 2 squared is what I want, but this times 5 is what we have. So like we did before, we're going to try to figure out what exactly we need to do to make that part go away. And it might make sense that just like we did previously, when we divided by that 4, what if we do the same thing, but this time divide by 5? That's going to make us have 1/5 times this stuff, which is 1/5 times the stuff down here. Those pieces go away, and we get the inside that we want. So this is the derivative of a function that's 1/5 5x minus 2 to the third over 3. And again, I'm going to hold off on looking at that just for now, and we're going to come back to that in a moment. And then we got this weird, crazy one that has an x in it. There's all kinds of stuff going on. And we end up looking at something that's really strange. So I'm just going to start with the function that's on the inside here. We know that the derivative of e to the stuff is e to the stuff. So the derivative going backwards, in other words, the antiderivative is going to be e to the stuff as well. So if we start out with, okay, we've got e to the 3x squared minus 1. I'm going to ignore that 24x just for a minute. And we were to take the derivative of this, just to see what happens. We've already done this, so it's okay. We end up getting e to the 3x squared minus 1 times 6x for the derivative of the inside. That's kind of similar to what we have here, actually. We've got 24x instead of 6x, but would it make sense to rewrite this as 4 times 6x times e to the 3x squared minus 1? So we have this function, but we just have 4 of them. That's kind of weird. Okay. So what this actually ends up being is the derivative of 4 times e to the 3x squared minus 1, which is still kind of a weird thing that's happening here. What I would like for us to notice is that in each of these 3 cases, part of this kind of goes away. And I could elucidate on this last one a little bit more carefully if I had thought ahead and have written this as 4 times 6x times e to the 3x squared minus 1 over 6x. And I think that's going to help us see something, because those are going to cancel out here. But dividing by that 6x, which is related to that 3x squared, dividing by this 5, which is related to that 5x minus 2, dividing by this 4, which is related to that 4x minus 5, we're dividing by the derivatives of the inside functions in each of these cases. Here that goes away, which makes that part kind of disappear. But in other places, that shows up really clearly. And it might make sense that if we do the chain rule forwards, we're multiplying by the derivative of the inside. And if we begin to do the chain rule backwards, we're going to divide by that stuff on the inside. So looking at a general strategy for this is going to end up giving us a process that we can kind of treat this going through the same steps every time. Because we have this stuff on the inside, and we know we're going to have to deal with that. But working through that is kind of a little bit trickier. So we have this process to make this a little bit easier for ourselves called U-Substitution. And the way that we do this is that we set some arbitrary variable, we tend to use u for this, equal to the inside part of this function. Because if we do that, we end up getting the square root of u. And that we know how to do an antiderivative of, because that's going to be u to the 1/2. So let's begin this process. So we got 3x minus 2. Cool. The only thing is I have a dx here, and I need my variables here to be the same in order for this to work. So what we're going to do is to turn this expression into something that we can get a dx out of. And to do that, I'm going to take the derivative of both sides. The derivative of u is going to be du dx. And the derivative of 3x minus 2 is going to be 3. Okay, so I've got to get rid of that dx. So let's get dx by itself. I'm going to have du is equal to 3 dx. I'm going to use some not great math to do this, but we're going to pretend that's a fraction, and that's okay. And then we're going to divide both sides by 3 to get du over 3 is equal to dx. Okay, so by doing some kind of side math, that gives us a dx to plug in here. And we end up getting, I'm going to write this as u to the 1/2 because we know that's going to make it easier. And then instead of dx, we're going to write this as du over 3. I would love to not have this as du over 3. So I'm going to move that forward and rewrite this as 1/3 u to the 1/2 du. Now we have a power rule. I'm going to increase this power by 1, so I'm going to have 1/3. U to the 1/2 plus 1 is going to be 3/2. And then we've got to divide by that new power. Okay, I'm going to simplify this a little bit. So dividing by a fraction is the same thing as multiplying by its reciprocal. Instead of dividing by 3/2, That's going to be multiplied by 2/3. 1/3 instead of u, I'm going to put a big space there just for a minute. We're going to put our original function back in because we said that u was 3x minus 2. So instead of u, I'm going to write this as 3x minus 2. At this point, we're done. We have found a function whose derivative is the square root of 3x minus 2. In practice, we ended up dividing by the derivative of the inside, which when we have numbers, that's not too scary for us to do. When we have things that involve lots of x's, that's going to be a little bit messier for us. So we have this process called U-Substitution. Whatever's on the inside, we set equal to u, and through that, substituted every piece of this in order to convert it over to u, so that we could do the antiderivative a little bit easier. Let's look at another couple of examples and see if we can understand this process of using this formal method called U-Substitution. I'm actually going to start in the one on the right to get us started. So I've got to figure out what's on the inside of this function, and that's going to be what my u is. And to me, this looks like I've got stuff squared. So if I take a look at the stuff that's on the inside, I'm going to set that to be my u. So u is going to be 4x plus 5. All right, that gives me u squared, which looks good. Then I've got the dx. I want this to be in terms of u. So to do that, I'm going to take the derivative of u and 4x plus 5. That's going to give me du dx. And derivative of 4x plus 5 is 4. To get dx by itself, I'm going to multiply it to the other side and divide by 4. And that's going to give me, I don't need dx over something. So if I multiply that to the other side, then divide by 4, we got du over 4. That's going to give us u squared and du over 4, which I tend to like rewriting by bringing that divide by 4 and write it as 1/4 in front of this thing. Okay. I could move that out in front of this integral if I wanted to. That might make it a little bit easier to see. This is just a reverse power rule, or I can leave that there, and we end up getting 1/4. I'm going to increase the power by 1, so we get u to the 3rd, divide by the new power over 3. I know that this has to be plus some constant, so we end up doing this as u to the 3. 4 times 3 is 12, and then plus c. Except now I've got to put my x stuff back in. So when I do that, we get 4x plus 5 to the 3rd over 12, and then plus c. Okay, so looking at this other one, it's a little bit tricky to see what's on the inside here. And the reason that that's tricky is because we have this notation sine squared of 3x. I'm going to rewrite that as sine of 3x squared. And then we got times cosine of 3x and then dx. This is a good example to talk about what happens if you choose a u that doesn't work. And the first thing that I notice here is that we end up with stuff that looks like we're on the inside here. The easiest thing for me to see on the inside, and this is not going to be the one that works, is going to be 3x. So I'm going to write u equals 3x. And when I do the derivative, we get du dx is equal to 3. So dx is going to be du over 3. When I go to plug this in, and again, this is an example of one that does not work, we get sine of u squared times cosine of u du over 3. And what I'd like you to notice is that that still does not help us. That doesn't make this something that we can take the antiderivative of easily, because I don't know a derivative rule for sine squared cosine of something. And we don't have any way to deal with this in terms of a reverse product rule. So when that happens, what that suggests is that we chose the wrong u. Okay, so let's go back to the drawing board. In this function, I noticed that sine of 3x is inside something squared. So I'm going to try doing that as my u. So sine 3x. Okay. Du dx is going to be cosine of 3x. We've got a chain rule there, so times 3. And getting dx by itself, we end up with du over cosine of 3x, and then I'm going to put a 3 out front so it's a little bit less confusing. Let's try plugging that in. So we've got u squared times cosine of 3x and times du over 3 cosine of 3x. What I'd like you to notice is that this other stuff here that's not the u ends up getting canceled out by the stuff that's on the bottom of the du. The really cool thing about that is that that creates a situation that suddenly we have u squared times du over 3. In other words, 1/3 u squared du, which is something that we know how to do the antiderivative of. That's a power rule, so it's going to be 1/3, and that's going to be u to the 3 over 3. I've got to add a plus c at the end, and when I plug my function back in, 1/3 times 3 in the bottom is going to be 1/9. U is going to be sine of 3x cubed, sorry, I was about to say squared, and then plus c. At this point, the problem is done. These two examples are other ones that just kind of help us see this process of U-substitution. This is something that it really does take practice to kind of get used to, and once you practice it, it's going to click at some point and become a process that's not too bad for you to use. One of the mistakes that I made when I learned calculus in high school was that I refused to learn this process and made myself kind of do these all in my head. Because of the way that my brain processes things, that worked out okay until I got to harder problems when I got to college, and I couldn't do that. So I had to teach this to myself on my own instead of learning it when I was asked to learn it. So I use that as kind of a warning to please don't do that.